Ryohei Kobayashi, and Assistant Professor of Center for Computational Sciences of University of Tsukuba in Japan. So I'd like to talk about OpenACC-Enabled GPU-FPGA-accelerated computing for astrophysics simulation. And this is our research outcome, and these people are my research colleagues, and on behalf of that, I represent our research outcomes. So first, I'd like to introduce our research background. So there is many accelerators, something in the GPU and FPGA and the DSP and etc. So the most popular player is the GPU, as you know. So because the GPU has a large scale SMT fabric in a chip, and the GPU equipped with high bandwidth memory like a GDDR5 or HBM2. So that's why GPU is very popular, but GPUs do not work well on the applications that employ the partial parallelism or non-regular computation, occurs warp divergence, or occurs frequent internal communication. So that's why we are focusing on the using of the FPGA for the HPC, because the FPGA can enable the true co-designing with the application, because the FPGA can become anything. Designs this circuit in an FPGA. So nowadays, the OpenACC-based FPGA development tool chains are available thanks to the FPGA vendors. And the high-end FPGA has a high bandwidth interconnect, which was equipped with 100 gigabps by the several channels, typically 4 channels. So this is a summary table of the each device's strengths and weaknesses. But the point is each device is the different strengths and weaknesses. So that's why it is important to compensate with each other by offloading the appropriate computation to the appropriate devices, computational devices, to offer the large degree of strong scaling, which means driving HPC more forward. So that's why we have the concept to make GPU and FPGAs perform the cooperative computation to accelerate the multiphysics applications. So we are focusing on the multi-scale complicated problems. These applications has various computation, include various computation within the simulation. So that's why it is very tough to accelerate the simulation speed by GPU only. That's why we trying to use FPGA to cover the GPU non-suited computation part. So it is reasonable to offload the massive parallel computation part to the GPU, and the CPU invokes the GPU computation kernel and the FPGA computation kernel and managing them. This is the charm concept looks like. So biggest challenge is to achieve the charm concept is programming, how to program the application making both devices perform the cooperative computation. So we already know that CUDA plus OpenACC mixed programming is possible to achieve the charm concept. But so the CUDA is for the GPU computation kernels, of course, and the FPGA is for the OpenACC is for FPGA computation kernels. But it's too much hassle that nobody wants to do the multi-linear programming, including me. So our approach to build the OpenACC programming framework for the multi-header devices to describe the GPU and FPGA operation in a unified manner. We built a comprehensive programming framework to make GPU and FPGA work together in OpenACC. So this is a collaborative research with Oak Ridge National Laboratory, FTG, and Jeff DeBeta's team, because that team introduced the OpenACC compiler, which is OpenACC compiler for FPGA, to enable the OpenACC coding for FPGA. So with a collaboration with Oak Ridge National Laboratory, we built key compiler system to support the FPGA and GPU unified OpenACC coding, which is MHOLD, a multi-header OpenACC translator. This MHOLD is already presented in the HLPP 2020 in June 2020. So MHOLD analyzing a single program in OpenACC and generates OpenACC code for GPU and OpenACC code for FPGA. And after that, the OpenACC code for GPU is compiled, the PCI compiler and the PCI compiler OpenACC, and separately. And after that, these object files are linked by the FPGA compiler and generate the executable file. The OpenACC generate the OpenCL code for the FPGA as well, and the OpenCL code is compiled with Intel FPGA SDK for OpenCL, and then the FPGA bitstream file was generated. And the executable file leads the AOCX file at the runtime. And the GPU and FPGA cooperative computation was performed in the GPU and FPGA platform. So our target, the application, multiphysics application is ALGO, which is accelerated radiative transfer on grid using octet-tree. This application simulates how the early-stage universe is created after the Big Bang. So the most characteristic point is to require the radiative transfer simulation combining two types of radiative transfer. One is the radiative transfer from the point source, and the other is radiative transfer from using a diffuse photon. That we are trying to accelerate ALGO code by adopting a charm concept as shown here. And this is the most frequent and complicated part. So there are two schemes in ALGO code. ALGO scheme and other schemes. So ALGO code has ALGO scheme and ALGO code has other scheme separated. And we have to combine these schemes to simulate the early stage universe within the ALGO code application. So ART method is to solve the radiative transfer from point of radiation source, as I told you. So ALGO method builds the octet-tree data structure for the distribution of the radiative transfer radiation source. For point of view from the target mesh, as shown here, it is treated as the same light source if the light source fell within the certain degree, as shown here and here. Thanks to that, so the effective number of point source is reduced from the n to log n. And the ALGO method is very similar to tree code in gravity simulation. So that's why it's very suitable for the GPU offloading. And each ray assigned to each CUDA thread, and then these computations are conducted in parallel. The problem is that the ART method. The ART method accounts for more than 90% of the ALGO code at first. The biggest problem is the ART method is not suitable for the SIMD style architecture like the GPU and FPGA, GPU or CPU, because the ART method has very different memory access pattern for the mesh data. Because there are several rate directions within the simulation, so causing the decrease in cache hit ratio. And ART method needs the atomic operation for the processing supermotion of the effect of the multiple rays on the shared mesh. So to avoid atomic operation, ray tracing along the red and blue light must be separately performed, but it causes the memory access pattern to become more scattered. So that's why we have decided to use FPGA to accelerate ART method, because FPGA can optimize the memory access pattern using the custom memory access logics. Before we are investing in the OpenACC-Enabled GPU and FPGA cooperative computation for the ALGO method, we performed a preliminary evaluation for the how much the OpenACC implementations achieved against the CUDA implementation. So at first, we'd like to know how OpenACC degrades the performance against the CUDA implementation. So which means this is a one GPU performance, there's no FPGA in this evaluation. So we use a single computer which is working at CCS University of Tsukuba, and the compilation flag is shown here. So as you can see, this is a preliminary result, and as you can see, there is almost no difference CUDA implementation and OpenACC implementation. So there are three parts of this result: the ALGO method, the ART method, and the others. The others is to solve the chemical reaction and radiative heat and cooling of each meshes. This computation is very highly independent from one another, which is very suitable for the GPU computation. So there is almost no difference between the CUDA implementation and OpenACC implementation. In ART method, the small mesh size is 73% and 96% of the CUDA implementation performance, and large mesh size is almost same as CUDA implementation shown here. So this is a mesh size of 16 cubic and 32 cubic, 64 cubic, and 128 cubic. As you can see, there is no difference between the CUDA implementation and OpenACC implementation, as shown here. But in small mesh sizes, there are almost degradation is because of the insufficient parallelism for the mesh data. So the current status is of the GPU and FPGA accelerated computation in algo code with OpenACC. So we confirmed the GPU and OpenACC-enabled GPU and FPGA version, the algo code comparison was performed successfully, and the execution result was correct compared to the CPU and GPU only execution result. But the performance is a problem. There are up to 850 times slower than the CUDA plus OpenACC implementation. So we need to redesign, we need to investigate why the performance is so poor than the CUDA plus OpenACC implementation. So with the correct optimization, so these results, GPU and FPGA accelerated result can be obtained, and this can be expected. So these results are reference our previous research, and this result based on the CUDA plus OpenACC implementation. So how to improve the OpenACC-enabled CUDA GPU and FPGA accelerated the application? So biggest difference to the OpenACC-based FPGA implementation is the spatial takes advantage of spatial parallelism. So OpenACC implementation has several OpenACC kernel to exploit the spatial parallelism, but OpenACC that generates the hardware engine in the OpenACC description is only one single pipeline, so which failure to take advantage of spatial parallelism. But OpenACC compiler supports the kernel-to-kernel communication, so it is required to redesign OpenACC implementation to generate OpenACC-like code using a channel. So here is the conclusion. So we built the OpenACC-based comprehensive programming framework to make GPU and FPGA work together. And the key compiler system is mHOLT. And we are focusing on the multiphysics application because it is hard to accelerate the simulation speed by GPU only. So our target application is algo code, and the offloading out method to the FPGA, and the other part is the GPU. The performance, there's almost no difference between the CUDA and the OpenACC implementation. But problem is the GPU plus FPGA implementation with OpenACC is very, very slower than the CUDA plus OpenACC implementation. So we need to redesign OpenACC implementation to generate the OpenACC-like code using channel. That's it. Thank you very much.